So proofs themselves could become mathematical objects that can be investigated by mathematical methods. But at that time, Hilbert hadn't formulated his program. Actually, at that time, he was still looking at founding mathematics on a version of Russell and Whitehead's Principia Mathematica. And then the finitist consistency program emerged a few years later. And, well, as you know, Hilbert's idea was to codify the whole of mathematical reasoning, or maybe a part of it, in a form of theory T, and then prove the consistency of T by finitistic means. Well, finitistic means here certain methods that are absolutely necessary for doing any scientific reasoning. And to carry out this task, Hilbert inaugurated the new mathematical discipline of Beweistheorie, the German word for what's now called proof theory. And as I already said, here proofs are investigated by mathematical methods. As to further consistency proofs, so in 1904, Hilbert had a consistency proof for a very weak theory of arithmetic. And then Ackermann, in his dissertation from 1925, he proved the consistency of a stronger system of arithmetic, which, among other things, incorporates functions you can define by primitive recursion. And looking at this from a later viewpoint, it turned out that in his proof he used a certain amount of transfinite induction, and it's a transfinite induction up to the ordinal. You take omega to the omega to the omega. And okay, so here already we have this kind of topic that the consistency of a theory in which you can formulate mathematics may be proved by some kind of transfinite induction. Now, this was then pursued much further by Gentzen, and Gentzen also used transfinite induction, and well, he could actually refer to Cantor's presentation of ordinals in Cantor-normal form. So every ordinal greater than 0 can be written as a sum of exponential terms where the base is omega. So its beta is of the form omega to the beta 0 plus 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 omega to the beta n, where the exponents, the beta I, are weakly descending. And this leads to the ordinal epsilon 0. Epsilon 0 has different definitions. It is the first ordinal bigger than 0, such that whenever you take something smaller, beta less than alpha, then omega to the beta is still less than alpha. And another characterization is that it is the least ordinal alpha, so that omega to the alpha equals alpha. Now it turns out that if you look at the ordinals beta less than epsilon 0, and if you write them then in Cantor-normal form, so you write beta as omega to the beta 0 plus 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 omega to the beta n, well, then it turns out that the exponents, these beta i's, are less than beta. So this is the case if beta is less than epsilon 0. And then, you know, these beta i's are less than beta, so they're also less than epsilon 0. And they again can be written in counternormal form. And their counternormal forms will then involve exponents that are less than beta I, and so on. And since this kind of decomposition into counternormal forms has to terminate after finitely many steps, you see that these ordinals can be coded in the natural numbers. So the ordering on epsilon 0 can be coded as an ordering on the natural numbers. And if you look at this kind of representation from a computational complexity point of view, it turns out that these present representations have very, very low computational complexity. Okay, so now Gentzen's result was, he was aiming at a consistency proof for full piano arithmetic, so first order number theory. And so what he did is he used a certain amount of transfinite induction. He used transfinite induction up to epsilon 0. And apart from that, because you can talk about epsilon 0 in a very basic fragment of arithmetic, much more basic than primitive recursive arithmetic, it turns out everything else that Gentzen applied beyond this transfinite induction was something that falls under the umbrella of Hilbert's finitism. So Gentzen applied transfinite induction up to epsilon 0 only for primitive recursive predicates. And besides that, the proof is entirely finitistic. Okay, and so this is kind of the birth event of ordinal-theoretic proof theory. So summarizing what Gentzen did again, so it can be split in two parts, namely F here standing for some theory that formalizes finitism, whatever that may be. For our purposes, this can just be primitive recursive arithmetic. And another part where Gentzen used the transfinite induction, PR, TI, epsilon 0, TI standing for transfinite induction, and PR standing for primitive recursive. So it's primitive recursive transfinite induction. And from these two ingredients, one deduces the consistency of PA. Moreover, Gentzen also showed that you cannot get it cheaper. You really need this transfinite induction up to epsilon 0. Okay. Now, this can be, this leads to a nice picture. So if you're interested in proving the consistency of various theories, maybe you can do it as follows. You kind of, you work basically in a finitistic theory, let's say like PRA, and then you have to figure out how much primitive recursive transfinite induction you need to show the consistency of a theory T. And so then the idea is that this ordinal that you need to do this measures the strengths of the theory. So this is very roughly the idea of the proof-theoretic ordinal of a theory T. I should maybe flash a warning here. One has to be careful here. And this way of doing or describing it is very compelling. It's a nice picture, but it's also a bit naive. Okay, all right. But anyway, so this is the guiding idea. Okay, now we have this ordinally informative proof theory, so, which just means proof theory that uses ordinals to measure and calibrate theories and other things. And in this area of proof theory, there are two main strands of research. And one strand is you use proof-theoretic techniques to eliminate cuts in proofs. I will come to that shortly. And these cut elimination techniques are very important, and there have been lots and lots of developments. And the other strand is, well, you have to measure these cut elimination techniques are applied to various proofs, finite proofs, but also infinite proofs. And you would like to measure the complexity of these proofs and keep track of manipulations you do on these proofs. So for instance, cut elimination incurs a cost, and you would like to measure the cost. And the cost is usually measured in terms of ordinals. And for that purpose, you need ever stronger ordinal representation systems. Okay, now just very briefly, the main system invented by Gentzen, in which one develops proof theory, it's the Sequin Calculus. Okay, just to recall, so here I'm using the two-sided Sequin Calculus. So we have two parts here separated by this arrow. Okay, so then these gamma and delta, uppercase Greek letters, they range over finite sequences of formulas. And the idea of such a sequent, gamma, let's call it gamma arrow delta, the idea is that gamma arrow delta should be read informally as gamma yields delta, which means more specifically that the conjunction of all the formulas in gamma, the antecedent, yields the disjunction of all the formulas in delta. So that's the meaning behind a sequent. And then with the help of these sequents, Gentzen was able to depict really the deep symmetries of logical inferences. And as it turns out, every logical particle, be they propositional operators or quantifiers, they come with their natural rules. So here we have, so the first bunch is negation rules. Then the next two, and since this is a two-sided Sequin Calculus, you will always have rules for that in the case of negation that start where the main formula, the thing that gets worked on, appears in the succedent, and then another rule where the main formula appears in the antecedent of the sequent. Yeah. And by the way, the notation beta comma gamma, for instance, just means that you add, not beta, that you add the formula B to the list of formulas in gamma. It just means appending the list. Okay, and then for every logical particle, we have these rules. So this is for implication. And going on, we have to go through all the logical particles. Conjunction is, of course, the easiest. So if you can deduce from A together with gamma delta, then you can also deduce it basically from A and B for any B plus gamma. And then rules for the disjunction. So here you have, there you have an A in the antecedent, and there's a B in the antecedent. In each case, they together with gamma yield delta, well then A or B together with gamma yields delta. And then, so this is the rule for disjunction where the formulas appear in the antecedent, and then you have corresponding rules for the succeedent. Okay, and then you go through all of these logical particles. For the quantifiers, we have the obvious ones. So here, for instance, you introduce a universal formula in the succeedent, and you can do it if you have already arrived at gamma yields delta together with FA. Then you can conclude with this inference for all right that gamma yields delta together with for all x fx. And of course, there's an eigenvariable condition here. The A, this variable here, is not allowed to appear anywhere else in delta or gamma. Yeah. Okay, so these are the rules for the logical particles. Then you have to start somewhere. And one place to start is with axioms where you just have identity axioms, A, arrow A. And a crucial rule is the cut rule, where you have two premises. And in the first one, the formula A appears in the succeedent. And in the second one, the formula A appears in the antecedent, and then you can cut it out. Yeah. So then this formula A disappears. This is the conclusion, and in the conclusion, there is no trace of A anymore. So a specific example is this here. So from B arrow A and A arrow C, you deduce via cut B arrow C. And if you look at the rules, all of the other rules of logic, they actually build up more complex formulas. So if you go from the premise of an inference to the conclusion, you see the formula that changes gets more complicated, but it preserves, in some sense, the formula where the inference started from. Yeah, and it's even more, of course, poignant in the case of propositional operators. So the cut rule is the only rule where something disappears. Okay. And then also, you need, for the bookkeeping, you need a little bit more. You need certain structural rules. These are boring rules that you can add stuff, weakening, that you can flip the order of formulas in the sequence. So this is flipping around exchange, called exchange. This is weakening. You can add formulas. And finally, you can contract formulas. So if you have a formula A appearing twice, you can contract it. And these rules are, I said they are boring, but they are, this is the object of study in what's called linear logic. Okay. And this very beautiful calculus, Sequin Calculus of Gentzen, also allows you to treat the intergenistic case in a very neat way. Namely, so what I introduced so far is the classical Sequin Calculus. The intergenistic Sequin Calculus is obtained by just one requirement, namely by requiring that all the sequence are intergenistic, which means that in the delta and the succeedent here, not more than one formula is allowed to occur. So this can be one formula, the sequent, or the empty sequent, no formula. And of course, it has if you require this, it will have some consequences. Some of the rules are no longer possible. For instance, contraction right disappears and exchange right disappears as well. And just to give you an example of a deduction in this Sequin Calculus. So here we have a deduction of the law of extruded middle. You start out with an identity axiom, A, arrow A, then you use a negation to move the A in front of the arrow here, behind the arrow. And then you can apply an OR rule to bind these two together. Yeah, and then you can do another OR rule and finally a contraction, and you end up with A or not A, excluded middle. Well, and as you see, this is not an intergenistic deduction because the formula A, and there's two formulas occurring in the succedent here after the arrow. But on the other hand, this deduction, as you can easily check, there is at most, at any moment in time, there's at most one formula in the succedent. And actually at this step, there's none in the succedent here. And we get a deduction of the implication there exists no x with fx implies for all x not fx. Now this is intergenistically valid. Okay, this just... Now Gentzen's result about his Sequin Calculus was the Hauptsatz from 1934. And what he proved was that actually the cut rule is superfluous. It can be eliminated. So given any proof in his Sequin Calculus, and the proof usually would have applications of the cut rule, well, all of these applications can be removed. And this gives a proof without cuts, also called a cut-free proof. Okay. And just to give the very rough idea here, the cut elimination theorem works by reducing the complexity of the cuts. So for instance, in the upper part here, we have a cut where the cut formula is of the form A implies B. And this can be, this piece of the deduction, view this as a piece of a deduction, this can be replaced by this part here, which is slightly more complex in a certain sense, but it's less complex because it turns out we have now only cuts with formulas A and formula B, whereas before we had a cut with the formula A implies B. And the formulas A and B are shorter in some sense than A implies B. And you see that if you continue this procedure, eventually you will be able to remove all cuts. Of course, it's not as simple as in this example here in general. It's just to give the gist of the idea. Okay, the Hauptsatz, Gentzen's Hauptsatz has an important consequence, namely the subformula property. So if a sequent gamma arrow delta is provable, well then by the Hauptsatz, we know it's provable without cuts. And this has the consequence that all the formulas that appear in the deduction must be, in some sense, subformulas of formulas in gamma and delta. So this is the property that of the Sequin Calculus, if the cut rule is removed, then nothing really gets lost. And it has a very simple property, corollary, so there cannot be a contradiction. The contradiction in the Sequin Calculus is exemplified by the empty sequent. Yeah. And okay, and then you can see the empty sequent where there's nothing. This cannot be deduced because if there was a deduction, if there were a deduction of the empty sequent, there would be a cut-free one. And then you can ask what could have been the last inference. And if the last inference cannot be cut, then there isn't such an inference, because all of the other inferences produce formulas. Okay, and then it turns out that Gentzen's Hauptsatz, and there's a misprint here, I forgot the T, could be used to infer all the main results of proof theory that were known at the time. And so, for instance, there is Hilbert's theorem that if you can prove in the classical Sequin Calculus an existential statement where R is quantifier free, then you can deduce a disjunction of examples, RT1 or RT2 and so on, or RTN. There's an extended version of Hilbert's theorem where you can have something in the antecedent, namely, if in the antecedent you just have purely universal formulas, so no existential quantifiers. And there's also the, you can also deduce the what's called the existence property for Intergenistic predicate logic. If you can prove an existential statement, and here there's no restriction on the R whatsoever, then there is a witness for this. Then you can find a term T so that RT is deducible. And then there are some requirements on gamma, of course. Also, another result is Hilbert-Ackermann consistency, so that's a criterion for a universal theory being consistent. And what also follows from Gentzen's Hauptsatz immediately is that if you have a geometric theory and you have a classical proof of a geometric implication in it, then there is also an intergenistic proof. Well, geometric theories are very, very common, actually. Most algebraic theories are geometric theories. Okay, so this Hauptsatz produced a wealth of results. Okay, now the question is, well, here we just looked at, we have looked at predicate logic, so pure logic, as it were. But most theories will have axioms, and what happens then? Well, it turns out that axioms are detrimental, so they're not good for the cut elimination procedure. Basically, it breaks down, and it breaks down, in particular in the case when the cuts come from axioms of the theory T. However, in many cases where one has a bound on the complexity of the axioms of T, one can say, well, at least we can do partial cut elimination. We can remove all the cuts that exceed the complexity of the axioms of T. Okay, so the partial cut elimination is also a very important tool in proof theory. It has been used in all areas, and also in bounded arithmetic, where it's called the witnessing extraction method. It underlies Robinson's resolution method, and so on. Okay, so as I said, if the axioms of the theory have bounded complexity, we can use cut elimination and can extract some information. But as you know, in the case of PA, the axioms have unbounded complexity. And this is due to the fact that we have the induction scheme. And so the formulas of the induction scheme can reach arbitrary complexity. So cut elimination fails here. And so Gentzen could not apply his method to the theory PA. So he wanted to prove the consistency of PA, and cut elimination directly does not work. But Gentzen had a way out, and this was a very smart way. So Gentzen imagined the following. So let's say you have a sequin calculus version of PA, and also assume, for the sake of the argument, that PA is inconsistent. Well, then PA will deduce the empty sequent. And so his strategy was to show that PA cannot deduce the empty sequent. And so what one does, one works with the derivation of the empty sequent and performs an operation on this derivation, which in some sense produces a derivation which is smaller in some sense. And the some sense is a bit mysterious. It's smaller in a certain sense. It's not the size of the derivation. It's some kind of complexity which gets measured by transfinite ordinals. In Gentzen's case, by ordinals less than epsilon 0. So what he did was he devised a reduction procedure R, so that whenever we imagine a derivation of the empty sequent in PA, then you apply this reduction procedure to D, and then RD is another derivation of the empty sequent in PA, but with Gentzen's ingenious ordinal assignment, it has an ordinal which is smaller than the ordinal of the original deduction D. And as you can see, if you do this, and you assume the assumption that there are no infinitely descending primitive recursive sequences of ordinals below epsilon 0, well then, from this result, or from this hypothesis, it follows that PA is consistent. Okay, just some results that Gentzen obtained. So as I said, from Gentzen's result, you get that the principle that there are no primitive recursive descending sequences below epsilon 0, you get the consistency of PA and a little bit more, what's called the one consistency. And also you can then show that the statement that primitive recursive descending sequences below epsilon 0 become stationary after finitely many steps, that's a mathematical principle which is not provable in PA itself. And it was Goodstein in 1944 who actually obtained a purely number-theoretic statement about sequences of numbers known as Goodstein sequences. And Goodstein almost proved in 1944, utilizing Gentzen's results, that the termination of these Goodstein sequences is not provable in PA. Okay, so these are some results due to Gentzen. Gentzen's assignment of ordinals to alleged proofs of an inconsistency in PA was really somewhat mysterious. And people wanted to find another way of proving this result, and preferably by using cotermination. But it required a dramatic switch, namely the switch from finite proofs to infinite proofs. Well, the idea of infinite proofs was already considered by Brouwer and also by Zermelo, who thought that the infinite proofs are the right proofs. And Hilbert, I think in his last paper, considered a rule, an infinite proof rule, where you have infinitely many premises. What it means this year means that assume you have deduced gamma arrow delta f0 and also have deduced gamma arrow delta f1 and so on through all the numbers n. So you have infinitely many premises here. Then you are allowed to deduce gamma arrow delta together with for all x, fx. So this is a rule with infinitely many premises, and the same a similar rule, because of the two-sidedness of this calculus, has to be there for the introduction of the existential quantifier in the antecedent. And Hilbert required that the f here, the formula, shouldn't have a large complexity. He only allowed primitive recursive ones. And then, not Hilbert, but then Schütte. Schütte was the last doctoral student of Hilbert. He went full scale into the realm of infinite derivations, and then he proved cut elimination for infinite derivations. So that happened in the around 1950. Okay, so that's the utilizing the omega rule in proof theory. And it turns out then that with this rule, if you use this rule, you get an infinite version of PA, which I call here PA sub omega. And so now we allow this infinite rule, and this also means that derivations or deductions will be infinite in this infinite system. And okay, and then we'll try to do cut elimination for the infinite system. And for doing cut elimination, one needs to keep a record of the length of the derivation, and also a record of the cuts that appear in a derivation. So we use this kind of notation here to notate that D here, the calligraphic D, is a derivation or deduction of the sequin gamma arrow delta. And the alpha here, the superscript attached to the turnstile symbol, indicates the length of the derivation. So length, and K indicates the max is a number, so that all the cuts appearing in the derivation have a length less than K. And for the purposes of the proof theory of PA omega, the K is always a finite number. Okay. And then if we write, and then this notation here means that, yeah, this notation means that this one here, the first one, means there is a derivation of the sequin gamma arrow delta in PA. Okay, and this notation here means there is a derivation in the infinitary system with the omega rule of lengths at most omega plus m and cut rank k for some m and k less than omega. So first of all, the finitary system, the usual proof system for PA, what's deducible there is also deducible in the infinitary system, and exactly with these measures, omega plus m and k for some m and k. And then the infinitary system allows cut elimination. Yeah. So the reduction lemma is the case where you have a formula A, and then you want to cut it. You have two derivations, and this is a situation where the A could be cut out. But if you cut out the A, then the K here would go to K plus 1, because the K is supposed to indicate that all cuts in the derivation are less than K. But A has exactly length K. And then this reduction lemma tells you, well, I can avoid increasing the cut rank of the derivation and still get rid of the A, but I incur a cost, and the cost is alpha plus beta. So this kind of symbol here, this sharp symbol, indicates the natural sum of ordinals. Yeah? And then this can be used to get rid of all the cuts. So basically, getting rid of a cut here, reducing the cut rank of the derivation from k plus 1 to k, results in a cost where you go from alpha to omega to the alpha. And then you can repeat this, and in the end you get rid of all these cuts in the derivation. And this result entails the consistency of PA, because, well, if an inconsistency were provable in PA, it would be provable in PA omega. PA omega has cut elimination, but there cannot be a cut-free proof of the empty sequence. What is disconcerting, perhaps, about this result is that you have to move from the finite realm into the infinite realm of derivations. Well, and then Hilbert's program was about doing things finitistically. It turns out there is a finitistic way even dealing with infinite derivations. But that's another topic I'm going to talk about today. Okay, right, now let's get higher. So a lot of mathematics can be done in PA, but well, usually we do mathematics in a system like set theory. Or another alternative is, that was basically discovered by Hilbert and Bernays, you can do it in what's called second-order arithmetic. And then there's also finite-order arithmetic. And okay, so here these, I just do here the second-order case. So here the idea is that these quantifiers for all x with an uppercase x, that they range over sets of natural numbers. And these rules are written down here. What they do is they encapsulate comprehension. So basically the rules, so this rule, for instance, E right, encapsulates that if you can prove F, and then you insert for each, for a variable V, you always, for a set, you introduce a class, the class of all V such that AV, if you can deduce this, well, then basically this inference encapsulates that this class here is a set. It falls under the existential second order set quantifier. Okay. And then Takuti in the late 1940s, he made a conjecture, which became called the fundamental conjecture on GLC, on this higher type Sequin Calculus with these particular strong comprehension rules. And Takuti wanted to show the Hauptsatz for this higher order logic. And this is what he wrote. Having proposed the fundamental conjecture, I concentrated on its proof and spent several years in an anguished struggle trying to resolve the problem day and night. So this is a quote I sometimes show to my PhD students when they start a project in proof theory. Okay, so second order arithmetic is a system where you have variables over numbers and variables over sets of natural numbers. And then it has a comprehension principle. It says that if you have any property definable in this language, let's call it P, then the collection of all the natural numbers n such that Pn holds forms a set. This is formally expressed by the comprehension principle here. Okay, and it turns out that these systems, formal systems, are quite strong. They can accommodate a lot of mathematics. And the usual stratification is you can stratify comprehension, and what you count here is the number of alternating second order quantifiers. Okay, so this means, so pi 1k means you have k many alternating set quantifiers, starting with a universal one, and then followed by a formula which is purely arithmetic, meaning there's only number quantifiers involved in this matrix here. Okay. And then this kind of comprehension can be stratified using this complexity. Okay. And then this leads to subsystems of second-order arithmetic, where you indicate how much comprehension you use. And it was already observed very early on that in most of mathematics you don't need very much of this comprehension. So Hermann Weyl in 1980 made an honest attempt to develop analysis with very modest means. As I said, Hilbert and Bernays observed that Z2 is actually fragments of Z2 are sufficient for ordinary mathematics. And this idea of looking at what you really need to develop certain chunks of ordinary mathematics was then pursued over the years by Pfefferman, Lorenzen, Takuti, and became a program, the program of reverse mathematics, with the leading figures being Harvey Friedman and Steve Simpson. And here the idea is that you take a piece of ordinary mathematics, say a theorem tau, and you would like to figure out what are the existence axioms needed in order to prove tau, and reverse is actually also the reversal that maybe that this statement, this theorem of ordinary mathematics also really logically encapsulates in a certain sense those existence axioms. Okay, and then this classification in reverse mathematics uses some standard systems, and just would like to indicate them briefly. So there is the weakest system is called recursive comprehension. So here you have a fragment of Z2, so second order arithmetic, where you're only allowed to use comprehension for classes that are given by a recursive formula. So you collect all those numbers n, satisfying Rn into a set where R is recursive. And a slightly stronger system is Witt-Koenig's lemma, which is nice for using compactness arguments. The third level is what's called arithmetic comprehension, where you can use comprehension just for formulas P. So the collection of all natural numbers n such that Pn is a set if the Pn is defined by a formula in which only number quantifiers appear. There can be second order variables, but no second order quantifiers. And then there is another system which is called arithmetic transfinite recursion. And usually the kind of classification systems stop at pi11 comprehension. So in pi11 comprehension, we can say that the collection of all n satisfying Pn is a set if Pn is a formula which starts with a universal set quantifier followed by something that is arithmetic. Okay. Now, just very briefly, so here's a bunch of mathematical results that can be associated with these systems. So the very weakest system, where you have recursive comprehension, you can associate with every countable field has an algebraic closure. The Witt-Koenig's lemma system, there you can prove the Cauchy-Peano existence theorem for solutions of ordinary differential equations. If you have arithmetic comprehension, you can prove both the Bolzano-Weierstrass theorem. And in the stronger system, you can prove something about abelian groups and so on. So these are just a bunch of examples. Okay. Before I say more about these 5 systems and how strong they are, Also, the five systems are sometimes called the Big Five. You will probably hear more about this in Sam Sanders' response. Before I can give you the proof-theoretic strengths of these systems, I have to go back to the other strand of ordinal-theoretic proof theory, namely developing representation system. Okay, recall that Gentzen used basically the representation of ordinals up to epsilon 0, and he could draw on Cantor's work. So where do we get stronger representation systems? Actually, Hardy was interested in constructing a subset of the reals of size aleph 1, and he gave explicit representations for all ordinals less than omega squared. Well, this is not a big feat in itself, but it inspired Oscar Veblen in 1908 to develop ways of presenting large initial segments of the countable ordinals. And he used the procedure of a derivative of a function on ordinals. So if you have an ordinal function f going from ordinals to ordinals, then what Veblen called a derivative, he called it and gave it the name f prime, is the function which enumerates all the fixed points of f. Okay, not every such function gives rise to another function f prime from ordinals to ordinals. They have to be normal functions. But anyway, so with the help of this operation, he defined a hierarchy of ordinal functions. Phi 0 is the first function in this hierarchy, and it's just the function that takes an ordinal psi to omega to the psi. And in the hierarchy, its successive stages, going from f alpha to f alpha plus 1 means taking the derivative. So f sub alpha plus 1 will be the ordinal function that enumerates the fixed points of the previous function phi alpha. And then for limit ordinals, you do something similar. So the phi lambda for lambda limit will be the function that enumerates fixed points of the previous functions, and namely if ordinals that are fixed points simultaneously of all the previous functions f alpha, phi alpha, sorry, for alpha less than lambda. Okay, and with this hierarchy, Veblen obtained a new normal form, and namely every ordinal, non-zero ordinal, has a phi normal form of this form. Namely, alpha can be written as a sum of terms couched in terms of the phi function, phi psi 1 eta 1 plus, and so on, plus phi sub psi n of eta n, where the terms in the sum are weakly decreasing, and moreover, eta I is always smaller than phi psi I eta I. Okay, and like in Gentzen's case, one would get an ordinal representation system from this if one could ensure that these ordinals appearing on the right-hand side are always smaller than the ordinal alpha. Well, it's a case with the eta I anyway. This is already ensured by this. But for the psi i's, this is not necessarily the case. And then you look at the first ordinal below which this is always the case. And this gives rise to another famous ordinal, which is called gamma 0. It was used by Pfefferman and Schütte in their proof-theoretic work in the 1960s. where they determined the limit of certain autonomous progressions of theories, how far these progressions reach. So progressions of theories were first introduced by Turing, and so gamma 0 is the ordinal up to which you have unique phi notations, below which you have unique phi notations. Another way of saying it is that's the least ordinal gamma bigger than 0, so that if you take ordinals alpha beta less than gamma, then, and if you then build this phi term here, this phi ordinal, it's still less than gamma. Okay. And actually, Veblen went much further than that. So he did not only introduce the phi function hierarchy, which is basically where you have two arguments. One is the subscript and one is the argument of the function. But he actually went transfinite. He allowed a transfinite number of arguments here, only with the proviso that at any given time only finitely many of these arguments are non-zero. And this big Veblen function actually gives rise to another representation system, which is actually called the big Veblen number. Okay, so much for that. Now going back to the systems here of reverse mathematics, you can actually assign ordinals to the first three systems. Well, it turned out that the first two systems are rather low in proof-theoretic terms. The ordinal is just omega to the omega. Then the system based squarely on arithmetic comprehension has the same ordinal as PA, it's epsilon 0. And then the next system, the fourth system, has exactly the strengths of the Pfefferman-Schutter ordinal gamma 0. So this, to name this ordinal, basically we needed the Veblen work from 1908. Well, and okay, Veblen went beyond gamma 0. You had this kind of big phi function with transfinite arguments giving rise to the big Veblen number. But it turns out that in proof-theoretic terms, this is still not enough to get ordinals to get an ordinal representation for the fifth system based on pi 1 comprehension. And okay, so here one needed a new idea, and I will only very briefly touch on this idea. And this idea presented a big leap in proof theory. It was done by Bachmann in 1950. And he had a very audacious idea, which I will only indicate very briefly. His idea was to name countable ordinals. You use uncountable ordinals. And the uncountable ordinals somehow serve the purpose of keeping track of functions defined by complicated diagonalizations. And what he actually did is quite complicated, and I will just flesh it up. So the idea that was crucial in Bachmann's approach was the use of uncountable ordinals actually to name countable ordinals, which appears quite strange, but it's a great idea. Okay, and with the help of Bachmann's approach, which then gave rise to what's called the Bachmann ordinal, or sometimes it's called the Bachmann-Howard ordinal, because Howard was looking for an ordinal to describe the system of bar induction, and he was amazed to find it in Bachmann's work. It's also sometimes called the Bachmann-Howard ordinal. And it turns out that this ordinal is the right ordinal to describe the strengths of a system of set theory. And the system of set theory is one that was quite famous in the 1970s because, so carries the name Kripke-Platek set theory. Well, because in some sense, independently, Kripke and Platek developed or singled out this set theory. Actually, the name Takuti could also appear there because Takuti at the time developed recursion theory on ordinals, and which basically also leads to the system KP. KP has no power set axiom, and the models of Kripke-Platek are the standard models. So the transitive models of Kripke-Platek are called admissible sets. And these admissible sets turned out to be a great research area that brought together several strands of mathematical logic, namely set theory, generalized recursion theory, and proof theory. The models, the chunks of the constructible hierarchy that are models of Kripke-Platek, they are called, so L alpha, if L alpha is a model of Kripke-Platek, it's called an admissible ordinal. So the constructible hierarchy is just the thing that Gödel came up with. Actually, there's a little bit of, he also drew on work by Hilbert. But basically what you do is you iterate the operation of definability through the ordinals. So you always add definable sets, definable over the previous chunks of the hierarchy. Okay, so Kripke-Platek set theory, just a very brief look at the axioms. So we have the standard axioms, extensionality, foundation, pair, union, you have the infinity axiom here. But then the crucial difference is that when it comes to separation, so in set theory we have ZF, we have full separation. Here separation is only allowed for delta zero formulas, where delta zero formulas are formulas in which all quantifiers appear in a restricted form. So they're either of the form for all x and b, or there is an x and b. Yeah. So no unbounded set quantifiers. And the same restriction is imposed on the collection thing. If we have that for all x and a, there's a y, g, x, y, well then then there's a set large enough to contain sufficiently many of these y's here. But in Kripke-Platek set theory, there's the requirement that the G here, describing the relation between x and y, should be a delta zero formula. Only bounded quantifiers are allowed in this formula here. Okay, and then, so the proof theory, the ordinal analysis for this Kripke-Platek set theory, uses the following ideas. It uses the Bachmann ordinal representation system B. And how is it used? Before I go there, so this was done first by Gerhard Jäger. At the time, there were similar ordinal analyses for systems of so-called inductive definitions. They're very closely related to Kripke-Platek. And so the idea is here you start with the Bachmann representation system. You view it as your spine of the ordinals. So the B become your ordinals. And then you build a formal constructible hierarchy of terms along B. So these terms you can just define in primitive recursive arithmetic. And then you switch to an infinitary version of Kripke-Platek, where the infinite inferences refer to these terms. So you have rules with infinitely many premises. And then in this system, KP infinity, you can prove cut elimination, not for all formulas, but for sufficiently many. So for sigma formulas are formulas where you can have unbounded existential quantifiers appearing positively, but no universal set quantifiers. And this requires a complicated technique of cut elimination, which involves so-called collapsing techniques, where, so in some sense, you collapse an entire proof. It's a bit like maybe the Mostovsky collapse of set theory transferred to proof theory, to give you an idea. Okay, and now, okay, so we have seen one system which uses an ordinal, the Bachmann ordinal, beyond what can be named by the methods of Veblen. Now I will give you a very, very brief history, repeating some of the history, namely, okay, we have Gentzen in 1936. Actually, to be precise, the ordinal epsilon 0, that only appears in the 1938 paper. Okay, then we have the Pfefferman-Schutte proof-theoretic analysis of how far you can get by certain autonomous progressions of theories. That involves gamma 0, and you get a certain, you can also devise a theory which is called predicative second-order arithmetic. And we have seen that it also corresponds to the third system in reverse mathematics, which is called ATR0, standing for arithmetic transfinite recursion. And then a very big step was done by Takuti. So he managed to get ordinal analyses of several systems. One of them is pi11 comprehension, and even stronger ones, also delta 1-2 comprehension. So this is the delta 1-2 comprehension. That's beyond the realm that's usually considered by people in reverse mathematics. And I also told you about the Bachmann idea of using somewhat uncountable ordinals or cardinals to keep track of complicated diagonalizations. It's a bit like Hilbert's idea of thought experiments. So here these large objects, they enter as thought experiments. In the end, you end up with something computational, representation system. But just to give you an idea of what these thought experiments somehow involve, in the case of Takuti, 1967, they involve omega many regular cardinals. In the case of the 1983 with Zugi, it involves epsilon many regular cardinals. And then there was a lot of work by Buchholz, Polos, and Sieg in 1977, or around that time, because, well, it stretches over several years. And then there's the idea of new many regular cardinals behind this as a thought experiment. There was a lot of stuff going on, complicated new infinitary rules by Buchholz, the big omega nu plus 1 rules. Polos invented a method called local predicativity. Girard came up with this pi12 logic. I already told you about Gerhard Jäger's approach to proof theory using the constructible hierarchy in proof theory, or a formal analog of that. And then there was work on a system which is much stronger than Takuti's system, which is basically delta 1-2 comprehension plus bar induction, which is the same as if you take the sigma 1-2 axiom of choice plus bar induction in second-order arithmetic. And you see, to get the ordinal representation system, the thought experiment involved an inaccessible cardinal even, yeah? And then there was work, well, I did some work then where I used the analog of a Marlow cardinal. Wilfried Buchholz used operator control derivations, a very important new tool. Then use of even the thought experiment involving weakly compact cardinals, and even more cardinals of a stronger flavor. And this culminated eventually in the ordinal analysis of a theory which is Pi-1-2 comprehension, the fragment of second-order arithmetic based on Pi-1-2 comprehension. And it's a long, long stretch to get there. Anyway. Okay. So now going back maybe to the pictures here, and this will be my final piece. So we already have seen this chart here. So the first 4 systems of reverse mathematics. So here we go, we gently go up, omega to the omega epsilon 0, and then from a higher point of view, even gamma 0 appears to be a rather small, benign ordinal. Then here we start at the bottom again, ATR 0, that's gamma 0, and then these double lines here. So the next system, the last system of the big 5, is based on Pi-1-1 comprehension, has this ordinal here. So these kind of notations somehow indicate how many infinite regular cardinals the thought experiment involved. So here it's omega many, epsilon 0 many, inaccessibly many. So the double vertical lines are supposed to indicate it's a long, long way to get from here to there. Yeah, long, long way. From here to there is not that a long way. It's just doing the same thing, just more often. So here you did something omega times, and here you did it epsilon 0 times. Yeah, and then, well, from epsilon 0 times to an inaccessible, that's quite a long way. Okay, and then it goes on. So here we start at what was at the top of the previous slide. So the system, basically delta 1-2 comprehension plus bar induction. And then you go up, 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 and this is kind of to give you an idea of, which of course doesn't work. Yeah, it's kind of the old joke. The infinite is very long. Especially towards the end, you go up, and then finally you get to Pi-1-2 comprehension. So it requires tons of new ideas to get there. Anyway, where are we now? So the current techniques of ordinal analysis, you can get up to delta 1-3 comprehension. Yeah. So now what about the thing that Takeuchi wanted to do, namely prove the Hauptsatz for second-order arithmetic? Well, after delta 1-3 comprehension comes Pi-1-3 comprehension. And this seems to be the current barrier. Of course, we would like to tackle this and surmount this barrier. There's also the question what comes after that. So having this kind of dream of being able to surmount it, what comes after that? And well, Pi-1-4, of course, but it would be strange if we had to climb then to Pi-1-4, Pi-1-5, and so on. Maybe it could turn out that Pi-1-3 comprehension is already the generic case that will tell us how to get an ordinal analysis of full second-order arithmetic. Okay, and here I would like to stop. So the Chinese Che. Thank you very much again.
Yeah, first of all, thanks for the great talk, Michael. I couldn't have done it better. I do have a couple of comments on some details here and there. So, well, first of all, starting with Hilbert Bernays' Grundlagen. So, what you see a lot in the American literature on logic is the following common misconception, namely that somehow you can find second-order arithmetic in one version or other in the Grundlagen of Hilbert and Bernays. And actually, so yeah, what are the facts? There are three logical systems, H, K, and L, defined in Supplement 4, which Hilbert and Bernays used to formalize math. Now, system H is, of course, for Hilbert, which is developed to the greatest extent. And then they say, well, you can also have this weaker system K. You can develop some math there, which they do. And yeah, the weakest system is really only mentioned, saying sort of like, yeah, maybe we could even go weaker, but they don't do much. And H and K, the main systems, involve third order parameters that are used in an essential way. So it's, I mean, in previous systems with Ackermann, Hilbert worked like fourth order or something. Now they're working sort of second order with third order parameters, but the third order parameters are essential. And a particularly obvious example is Pfeffermann's mu, which by the symbol mu already appeared in Hilbert and Bernays. So Pfeffermann's mu is the least number operator. And yeah, that's how Hilbert and Bernays define it. If there is an x such that a of x, mu of x will find it. And it's the least one, so because if a satisfies a, then yeah, and so on. So yeah, this is German. And that's how you can find it, I guess, on page 399. So they use these third order things, third order parameters. And system H even introduces, I've called the new functional. I've written it down here in modern form because it's a little, the formalism is a little heavy. If there's a function satisfying some formula A, nu of f finds it. And of course, I mean, if you have these functionals, you can introduce Z2 style comprehension, but comprehension is never mentioned. It's actually a fundamentally higher order system. And so, yeah, I just wanted to make that clear. Now, of course, you can raise the question, which has been raised by Kohlenbach, for example, is second order arithmetic enough? Now, third order objects can be represented or coded in the language of second order arithmetic, and it actually works really nice for continuous functions. Because Kohlenbach, based on a construction by Dach-Neumann, has shown that if you code continuous functions, if you represent them in the language of second order arithmetic, it doesn't really change the reverse math of WKL and beyond. Simpson is, of course, very grateful for this. But the problem is that's where it stops already. If you go to Riemann integrable functions, which means continuous almost everywhere and bounded, Riemann integrable functions, if you code those up, then you're changing reverse math a lot. This was shown by Dach-Neumann and myself. An example, the convergence theorem for the Riemann integral, proved by Arzela in 1885 and implicit in Denis 1870. If you have codes, a very weak system, namely WWKL can prove it, weak König lemma. If you formulate this without codes, you need comprehension axioms at the level of C2 if you want to prove this. So already for Riemann integrable functions, things can be very, very different in strength, whether or not you use codes. So yeah, ordinary math. I mean, I would call this a theorem of ordinary math, but yeah, somehow you need a lot of comprehension to prove it. Without codes. With codes, it's fairly easy to prove. And this is in a paper by Dach-Neumann and myself. It's on the archive now. Maybe one day it will be published for being unspeakable. Yes. Now, another thing, Michael mentioned countable, and yeah, many theorems in reverse math are actually formulated using, saying countable. And Simpson and Hirschfeld in various places even say this explicitly. Well, reverse math studies objects that are countable or can be countably approximated. Countable, 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 ordinary math, la la la. Countable, of course, means enumerated by a sequence. But yeah, what happens if you use other third-order definitions of countability, like Kuhnen's from Kuhnen's set theory book, injections to n, or bijections to n? This is Erbache-Kiech, the set theory textbook. Now, this is not, as the Germans would say, Spielerei, because Borel formulates Heine-Borel using countable collections. So in this book, his thesis, I guess, or based on his thesis, Leçons sur la théorie des fonctions, he talks about countable collections when he formulates Heine-Borel. And Heine-Borel is one of those things they study a lot in reverse math. And if you use these items, oops, that should be 1 or 2, they're much harder to prove than the second order version. So if you don't use enumerated by sequence, but actually Borel's definition based on countable collections, either of these, then it becomes much harder to prove. Heine-Borel becomes much harder to prove, yes. And again, you need an axiom at the level of second order arithmetic. And I'll give you a nice example, Bolzano-Weierstrass. In reverse math, you have theorems of this kind. If you have a sequence in Cantor space and a function from Cantor space to Cantor space, the supremum exists. And this is actually equivalent to ACA 0. Yeah, you can restrict to continuous f, and then you can work in the language of second order arithmetic alone. But it doesn't really matter. You can have higher order f. You can just have codes for continuous f. It doesn't matter. This is pretty robust. The supremum of a sequence that is bounded above exists. That's equivalent to ACA 0. That's well known. Now, let countable mean injection to n, and we can say, well, what about a countable set in the Cantor space? This supremum, of course, also exists, but then you can already derive pi12 comprehension from this version of Bolzano-Weierstrass, plus a higher order pi11 comprehension. And pi11 comprehension is, yeah, you know, but the higher order version involves the Suslin functional. Instead of comprehension, you have a functional that decides pi11 formulas. So from pi11 comprehension, you can go to pi12 comprehension by just adding the Bolzano-Weierstrass theorem for countable sets in Cantor space following Kuhnen's definition, namely injection to n. So whether or not you work with sequences or countable sets makes a big difference. So yeah, you know. And then finally, and then I promise to be quiet, I wish to talk about another shift of emphasis relating to proof theory. That other shift of emphasis, Kohlenbach's proof mining is well known, based on Kreisel's unwinding program. It's a shift of emphasis from consistency proofs foundations to applications in mainstream math, which is great. I wish to talk about another emphasis, which I think is interesting. If there's one thing we learn from reverse math is that sentences of pure math behave as pure mathematical sentences, so Heine-Borel, Bolzano-Weierstrass, they behave much nicer than purely logical sentences, like any sort of, the consistency of I sigma 17 has certain properties, but if you have a formula that somehow expresses a theorem from math, it tends to behave much nicer. I mean, the big five phenomenon and all that. I think this is similar for proofs because I've been looking at reversals and recursive counterexamples in second order arithmetic. And with minor modification, you can lift these to interesting higher order proofs. So there's no way you can lift arbitrary proofs from second order to higher order arithmetic. But a specific proof, namely reversals from reverse math and recursive counterexamples. And as an example, Specker sequences are well known. They give rise to a recursive counterexample to sequential completeness. And there's a proof, there's a reversal in reverse math. With minor modification, you can lift these kind of proofs and you can generalize this to Specker nets. Nets being generalization of sequences to index sets of arbitrary cardinality. This you can find on the archive too. But so my main point is that instead of looking at what can we say about arbitrary proofs, it might be worthwhile to look at specific proofs from the literature. And this has been relatively successful, I would say. So that's all I have to say. Thanks for the great talk, Michael.